Hi everyone. For some weird reason, my screen recording software doesn't recognize me as a registered user, so it stopped my recording after 10 minutes. So I'm gonna continue. So for this question, we talk about four will be a zero. The cost of going to four will be zero because we started from four, and then going to five, going to one, and going to zero. The cost will be one because they are accessible from four in one hop. But how about two? So for the two, there are two possible passes. It can be 4, 1, and 2, or 4, 0, and 2. But we are going to take the 4, 0, and 2. The reason is once we export the 4, and then we are going to enqueue 3 nodes. 0, 1, and 5. And because we say if we have the multiple nodes and then the smaller value goes in first. So we are going to enqueue 0 first and then 1 and then 5. So when we are expanding the node 0, we are going to see 2. So we are going to enqueue 2 and say the 2's parent will be the node 0. Going to node 0 first, and then node 0 will tell you how you can go to node 2. So this will be 2's parent is guaranteed to be a 0. So for some of you guys, and you make a mistake here. Okay? So the next question, hash table. And this question is really easy, and we just have all those keys, and then we want to use we want to use the take the coming key and then use this key and mode 11, and then to give you the corresponding slots on this hash table, and then we are doing chaining. So this means, and if you have a value, and then you are going to use the 0 as the start, and then the first node in this linked list is going to be 33, and if you have 44, and then 44 will be the next node after 33. Okay, and then how do we do a search? How do we do a deletion? Well, this is an interesting question because then, for example, I'm asking you to delete 44. So number one, you have to figure out if I'm looking for 44, which linked list do I need to look at? So we have to apply this hash function again, and this hash function will tell you if there is indeed a 44, and the 44 will be on the slot of 0. So when we are visiting the slot 0, and there are three cases we have to consider. So number one, if we go to the slot 0, and then this slot 0, on this slot 0, there's no linked list at all. What is going to happen? So, in here, we do have a linked list. But if we go to the 2, and then there's no linked list at all, right? So in this case, then, if we see, we want to go to the head of this linked list. But this linked list is empty. And then we say, okay, no, there's no such a value. And or another case could be, we have to do a search. We have to do a search on a linked list to find the corresponding value. So in this case, and say we want to look for 44, and then we do have a linked list. And on this linked list, we have to visit all the values to find the value we are looking for. So what if we don't have 44? And then we go through all the linked lists, no 44, we return a false anyhow. But the case 3, what if we do find this 44? And then how do we kill this 44 from our linked list? So, we are dropping a node from a linked list. And do you guys remember how do I do that? Say, we have one node, and then we have another node, another node, another node. Okay, so I'm going to say this is the linked list. So, and then originally I'm going to have a head. Okay, so we have a head, and then this head points to the first node, and then first node points to the second node. Okay, so what if I have a node to be deleted here? So let's assume that I have 44 here. So how do I delete this 44? So the trick will be I need to use 2 pointers. So I'm going to use a pointer called current. So this current will be a pointer that help me find the node I'm looking for. And then I also have another pointer called farmer. So this will be my farmer. So this former pointer will tell me where is my former node. So once I'm using the current cursor to find the 44, and then what I want to do is this code saying, well, I want to set the former next to the current next. That is, I want to update this reference to the next node after the current. So this current node is skipped from my linked list. This is how we can get rid of a node from a linked list. Okay? So the next question, well, dynamic set. So I'm proposing two different ways to do the dynamic set. So number one, singly linked list. So for the single linked list, I mean for the linked list, well, it only go one direction. So the head from the head to the first node, and then from the first node to the second one, and then the third one, the fourth one. Okay, so well, there's no reference back, say from the last node, and then we can go back, and then go all the way to the head. We don't have this. Okay, so how do we? And then this is also a sorted single linked list. So where is the minimum value? The minimum value is the first node, so it's a constant time. And then how about the maximum? Well, I say it can be 1 or n. So it is 1 if you do have a tail cursor. So a tail cursor could be like this. So we have a tail cursor, and this tail cursor is always points to, well, I think I want to get rid of this tree first. Okay. Okay. Yep. So let me kill this content first, and then this tail always points to the last node. So if we have a tail, and this is a sorted linked list, and then using this tail, we do get the largest value in a constant time too. This is why we say this can be a 1. But what if we don't have the tail? So if you don't have the tail, and then you have to do a linear search. So you started from the beginning, and then you go to next, go to next. So well, until you go to the last value or last node in the linked list, and then you find the largest value. And in this case, and then it will be n. Okay, and then how about insertion? So for the insertion, well, we have to maintain a sorted linked list. So we have to hold this value, and then we have to say, okay, should this value between those two nodes, or should the value between those two nodes? Say, let me put in some of the values here. Say this is 11, this is 22, and then this is 55. Okay. So what if I want to insert 33? So to insert 33, we have to see, okay, is 33 a good fit here? The answer is no. How about here? 33 good fit, and yes, and then I'm going to insert the 33 here, right? So, well, in this case, I do have to go through all the possible locations that I can make this insertion before I can find the right value. So this will be a linear time. And then deletion. So deletion, assuming we have already found this node, and then we just update the cursor from the former to the current next. So this can be done in a linear time. And how about search? Well, the search, in the worst case, we have to go through all the values, so it will be O(n) again. And then how about the RB tree, red black tree? So for the red black tree, and all of them will be a login. And we didn't cover the deletion, so I'm striking this cell out. Okay, so the next question. Well, we are assuming that we are going to do min and max 10% of time, and then we are going to do a search 70% of time, and then insertion 10% of time again. And well, when this system starts, and then it will load it will start by loading the n values into the dynamic set, and then this n will be a large enough number. Okay, so in this case, well, what I'm trying to discuss is, well, which one will be better? So, well, and to analyze this formally, and what we can do is, well, if we just want to consider, for example, 100 actions or 1000 actions using both of the implementations, and what is going to happen? So, well, 10%, and then we are going to do this one, And then I just assume that this the C1 will be the constant cost of doing a minimum and then in a singly linked list, a sorted version. So and then the expected running time will be zero point 0.1, which is 10%, and C1, 0.1, C2, and then 0.7, C3, and it will be an N here because this will be linear, and then 0.0, 10%, and C4 and N. Okay, so this 0.1, 10% is going to be a constant, and this 1 will be a constant too. So for this action, well, this will be a O N if we drop all the constant. And similarly, how about the red black tree? For the red black tree, and then it will be, well, it will be 0.1, and then constant 1, C1, and then, well, log n. So everything will be a log n here. So in this case, well, if we drop all the constants, well, for the expected processing time for a action on average, it will be a O log n. So, well, this means it doesn't really measure the probabilities. Well, because the probabilities will be dropped anyhow, but you will end up with an ON on average action for a linear linked list implementation. And for a red black tree implementation, it will be a O in log n. So this means, well, O in log n is better. Okay, so this is my solution to the midterm 2. Well, and then from now to the final exam time, if you have any requests, you want to me to record a video showing you or explaining an algorithm on a different example, and shoot me emails, and then if I have time, I will make more of this kind of videos. Okay, bye.